The third method of controlling enzyme activity is the method I refer to as activate and deactivate. Cofactors are molecules or atoms that are involved in controlling enzymes. They can be as small as a single ion or a single atom, or they might be the size of a small organic molecule. Either way, they must be attached to the enzyme to complete the functional structure of the enzyme. Some cofactors are classified as inorganic, and those are ones that are not carbon-containing. Examples would be like zinc, iron, magnesium, calcium, potassium, things like that. Things that sound like they belong more on a periodic table than inside a living organism. But you recognize these as things that are important in your diet or in the vitamin supplement aisle. The other cofactors are classified as the organic variety. They are carbon-containing and are usually small organic molecules. Sometimes these are referred to as coenzymes, but more commonly you'll recognize them as what we call vitamins. So the inorganic cofactors make up the mineral part of your dietary concerns, and the organic cofactors make up the vitamins. So vitamins and minerals is what we're talking about here. But these small atoms and molecules are there to actually turn on your enzymes. So if we go back to our illustration of a basic enzyme, some enzymes, like the one on the left, are made in a complete fashion, where they're able to function and catalyze the reaction the moment they are produced by the cell. But it's possible to make an enzyme incomplete, missing a single tiny required part to make it work. In that case, that missing part is referred to as the cofactor. Here in my diagram, without the cofactor, the active site is incomplete, and incomplete active sites cannot catalyze reactions. Once the cofactor has been attached to the enzyme, then the active site is complete, and then the enzyme can be considered to be turned on or functional once attached. An enzyme that has an attached cofactor functions like any normal complete enzyme, taking substrates into the active site and producing products. Now, if the cell decides at any time it wants to turn this reaction off, instead of destroying the enzyme or changing the reaction environment, you can specifically just alter the function of this very particular enzyme by itself by simply removing the cofactor. So this is like the on and off switch of the enzyme. Think of it like your car is made 99.9 complete. The only thing that will prevent it from functioning or turning on is the key. So cofactors can be also thought of as like little keys to the enzymes. The right key turns on the right enzymes, and so on. So each enzyme will have a specific cofactor necessary to turn it on. Continuing with activate and deactivate as a method of controlling enzyme functions, another method is called an inhibitor. Molecules that bind to an enzyme to basically turn it off or to make it non-functional are inhibitors. Competitive inhibitors function by attaching specifically to somewhere on the active site. Non-competitive inhibitors attach to somewhere other than the active site. In this illustration, competitive inhibitors compete physically for attachment to the active site. So in the presence of substrates, there's an equal probability of an inhibitor attaching to the active site or the substrates. If the substrates and competitive inhibitors are an equal concentration, then there's going to be an equal probability of either entering the active site of any enzyme. If a competitive inhibitor ends up in the active site of an enzyme, it will block and prevent any substrates from entering. So once a competitive inhibitor attaches, it shuts down that enzyme from being able to catalyze the reaction. Some inhibitors are non-competitive, which means they do not fight for the active site. Therefore, in lower concentrations, non-competitive inhibitors can attach to a site outside of the active site to render the enzyme non-functional. When attached, in this illustration, it warps or changes the shape or the positioning of the functional groups in the active site. Once significantly changed, the active site, not having its proper conformation, will now not be able to accept substrates. So non-competitive inhibitors can effectively shut down or slow down chemical reactions by attaching to somewhere other than the active site. Another form of activate-deactivate comes from what we refer to as allosteric regulation. And this is a form of control that only applies to very specially shaped enzymes called allosteric enzymes. And they're different from others in that they are made in a way that they can constantly alternate between an active and an inactive form, or conformation. Allosteric sites are also present on allosteric enzymes, and these are places or surfaces where other molecules can be bonded, called allosteric activators and inhibitors. In a diagrammatic form, we can show an allosteric enzyme looking something like this. On this side would be our active site, and on another surface there would be a new place of recognition called the allosteric site. The way that this enzyme is made, it physically has the ability to change shape, and it will constantly change shape, wobbling back and forth between an active form, like on the left, and an inactive form on the right. The one on the right, when this shape is attained, the active site will be incorrect for the reaction. So in this case, the reaction is off, and on the left the reaction, or the enzyme, is turned on. So at any one moment, the enzyme may be on or off, and probably 50-50, 50% on, 50% off at any one time. If an allosteric activator is present, it can attach to the allosteric site. If this happens, the enzyme will then be converted to being in the on position 100% of the time. So now the reaction rate will actually steadily increase compared to when the enzyme is out of the presence of the allosteric activator. Allosteric enzymes may also have allosteric inhibitors. So it's possible for a different molecule to bind to the allosteric site, and if this one attaches to the allosteric site, it'll lock the enzyme into its non-functional conformation. If the enzymes are all converted to this form, the non-active form, by attachment to allosteric inhibitors, then all of the enzyme reactions will cease. None of the substrates will be able to enter the active site because none of the enzymes will have the correctly shaped active site. So allosteric inhibitors and activators can modify how quickly a reaction occurs by changing the reaction rate from medium to either full speed or off. And different concentrations of allosteric activators and inhibitors can create a variety of speeds of reaction in between the case of full on and full off.